So in this chapter, it's a kind of means mix and match. And before we going to means start a formal and mature discussion on Lyapunam, forget about what I told you in lecture number probably 13 or yeah, probably 13. What I told you in 13, that is the basic tools you should know, or you should means accumulate that knowledge from your BTech or undergraduate course. However, uh, we cannot deny the fact that all of you are coming from the cross background, so and from different institutions. So, and there is no such means, as I told it thousand times, that there is no such obligation, and it should not be on that your the undergrad college that they would prepare you or means impart all the prerequisite knowledge in you so that you become means exactly compatible with our present course that we are dealing with, because we have certain objective in our mind, rather I have certain objective in my mind, and I would like to train you in that way. And no way, this is actually an idea of pluralism, like your approach of addressing a problem towards nonlinear control, what the idea or the word control engineering evoke in you, or what my idea of control engineering evoke in me, this can be completely different. Well, when I am quite happy with uh, theoretical approach, doing theoretical analysis, theoretical rigors, you might be means find it extremely boring and means like kind of means a job that suits more to applied mathematician than that of control system engineering. Your idea of control system engineering may be doing exactly that, dealing with the real life problem where you just need to know mathematics as little as you should know, and you should try to address a particular problem instead of formulating a theory. But this is the beauty of control system engineering. That is why we always claim, even if you go to IEEE Control System Society, this is the this makes this special means subject so special, that control system is ubiquitous. It finds its application in all the sphere of your life, even in your daily life, from your how you wake up, how you go to bed, all these, all your spheres of life, knowingly, unknowingly, you are applying control system engineering. So, without means chanting how good it is or how generalized it is, how much you can find it. Let me follow my way before I go to that formal discussion of lab now. Today, in this lecture, I am going to discuss that how, in case of linear, we know in case of I am doing a generalized analysis, that continuous dependence of, this is very important, like we should know that in which case or how the solution will be continuously dependent on initial condition and parameters. It is very interesting to note, I have mentioned 2 points, and for linear system it is quite obvious. Like if I give you an RLC circuit and ask you to form its like, without wasting much time, let me directly write the equation for series RLC circuit. What you have is like uh, x1 by L minus, where this U is your input voltage. So this is the means, if I have not made any mistake, probably this is your the equation of your that describes series connected RLC circuit state model. Even if I make mistake, that also won't stop me to deliver the idea what I'm trying to deliver you. The basic idea what I'm trying to deliver you, that intuitively you can understand that this differential equation, the parameters, they are in such a way that these one, if you take some value like say x1 0 is equal to 5 volt and x2 0 is equal to 0, you will see that whatever final equation you will get, or means final means obviously if R is there, and it depends on your voltage also, which type of voltage you are applying. But whatever equation you are going to get, the solution will definitely contain a part that is perhaps in your means state space analysis you have already learned that in your state we have two part of the solution. One is transient, another one is steady state, and this transient part is completely governed by the initial condition. So there is no such rocket science or something like very incomprehensible fact involved here, that you can have a difficulty in understanding that in case of linear system how it is. But we will investigate and try to make it more generalized and understand that in case of nonlinear also how special it could be and what are the clauses that must be satisfied. In addition, that is quite obvious for linear system. Like if I change this C, this R, this L, I can understand that what type of effect they are going to means impart on our system, and obviously that solution nature, solution trajectory will change. Like for ease of understanding, let us make R is equal to 0. What you would have for R is equal to 0, that will become a completely oscillatory circuit, right? So that is the beauty of the linear thing, that you can very easily identify that how one parameter is going to govern the entire solution, and obviously the solution is dependent on the parameter. However, in this case it is not that easy. So this is now we'll investigate by understanding two theorems. Actually, like if you, and again if we talk about initial condition, one thing I would like to specify more clearly, that if we write the equation for from which equation we started, like an equation of the form x dot is equal to f of t comma x, or you can write it like x dot, that makes more sense, and xt naught is equal to x naught, where x belongs to Rn. So in that case, if you solve it, like for sake of simplicity you can also reduce it to like x belongs to R1. Whatever be the case, that you can write xt is equal to x naught plus integration t0 to t f of s comma x. Here we need to include this ds. So it is obvious that it depends on t0, and as I have mentioned it 1,000 times, that we can show everything by means of mathematical argument, by means of mathematical rigor, but for us, at least the approach I am trying to follow, it is that to develop an intuitive sense inside you, rather than making you a mathematician, or means develop a confidence in you that I can do any sort of mathematics, I can develop any sort of theory. At least I am not capable of delivering you that much knowledge base. But what I am capable of doing, and I believe that if you try a little, you will be able to hope with it is that if you try to develop your sense of intuition as an engineer, it is very very important. Why I am means just like ranting over this for this rant, whatever I am telling you for so many classes, that only one thing is very important. You please as an engineer develop your intuition, because once you develop your intuition you can apply it to your practical problem. Also you can understand, means not completely, even if not completely, but lion's share of any research article you can understand by applying your intuition. So that is very important. Obviously getting acquainted with the mathematical tools is very important, but due to time shortage it may not be possible for us to learn about all those things, but you should develop the intuition. Now, think about this, that at any point, if we consider that we have a solution, like a solution, let yt be a solution of and this solution starts at and we define this solution on a compact time interval. So what is the essence of using this terminology compact? Say compact, from topological point of view we can provide a detailed explanation. There are steps to study the compactness, but as a layman what you can understand that a compact set is like, if you consider real number, it is compact. That means it is means you are not able to like indistinguishable, they are not countable, they are compact. But if you consider that one, like, so before proceeding, let me just tell you what makes a set compact. Compact means a set that is closed and bounded. If any set you see that it is not closed or not bounded, then it cannot be compact. Like this is also a very means what can I say? It's a very childish definition of defining compactness of a set. But if you want a more formal definition, I am trying to give you just, but I'm not sure that how much you could gather from it, because that definition involves the idea of sequence. However, instead of wasting time, let us try to give you some idea about compact set. That compactness is like, you can say that how to figure out like good example. Just hold on a minute. So as we are going to mostly deal with real number, let me write it for real number, that a set is a set of real number is called every sequence every sequence in S has a subsequence that uh, converges to an element contained in S. So in this regard, I would like to mention a few things like there exist sequences that are bounded but not convergent sequence. Like if you take a sequence that is so you will get an oscillatory sequence between -1 +1, and it cannot become unbounded, but at the same time they do not converge to any particular point, right? So they are not converging sequence. We have a technical term here. Just a minute. Now, what is Cauchy sequence? Cauchy sequence is not only bounded, but in Cauchy sequence, you claim it to be like after a certain means tail, like if you are saying it is say this sequence has capital N number of element. Now this n could be infinity, or say infinite sequence, that infinite number of elements are there. For your understanding, let us consider a case of damped sinusoid. So what is common here, that say if you take any point, say now you discretize it and you pick up points, you can select your sample interval to discretize this analog one, and you will get some equidistant point over here, and these points could become a member of your sequence. Right. Now, these points for any particular position, like n, say n is equal to some, uh, if you select the sample in such a small size that by this time you are having already 10,000 sample, what you can claim that once you have something, uh, you have m and small n greater than n, then the distance between xm minus xn, absolute distance, is less than a certain number epsilon. This is the property of Cauchy sequence, and more you proceed, then means in a literary way you can say that a sequence where the members get close to each other with time, means with progression, the members become close to each other, that is Cauchy. And what is a compact sequence? In a sense that, suppose, let me take one example of a sequence that is also a very popular sequence. It is like sequence members are defined in this way. So we started with x1 is equal to 2, right? And then we have to apply this formula, and what you see that you will be means surprised to note that this sequence can be present in a means you can collect the element of this sequence from uh, your rational number system, like all these individual xn will belong to rational number system, but the they will converge, like the final element n, limit n tends to infinity, this sequence will converge to a point that is root 2, that is not included in this cube. So this set is not compact and complete. Like here you can see that it is not getting means wait, this is one way out anyway. So for the time being, compact is something means forget about what mathematicians says. It is like a very dense set that is closed and bounded by its own composition. So what we are trying to do, that it was like we started with an equation x of t is equal to x naught plus t naught to t, then f of s comma xs ds. Then we claim that we could have a solution like yt is equal to, that is having initial value yt naught is equal to y0, and this could be a solution, and this solution depends continuously on t0. It's guaranteed because t0 is present in the equation. However, what we can say further, that if it is the solution continuously depends on y0 starting at any nearby point defined on the some time interval, right, the same time interval, and remain close to each other in that interval, we can make a precise statement in line of epsilon delta statement of continuity, like given epsilon greater than 0, there exists delta greater than 0 such that for all y naught in the ball, like for all z that belongs to the ball, x belongs to Rn such that norm of naught minus y naught less than delta, and the equation for all z0 actually means this one is corresponding to the initial point at your solution space, or means your range space. Now what we are trying to do, that it's very simple thing, that the how to write, yeah, this, if this is the case, x belongs to Rn for all, this is for our means domain we have specified. Now we have to specify the epsilon for the range stress, so we could write it like we have a unique solution of unique solution zt depend on time in between t0 to t1 such that we can have this the zt minus yt is your less than epsilon. So what is that way I have defined? Like we pick up another point z naught that belongs to a ball. How that ball is defined? If your original system equilibrium point is x naught, then that x naught is for system equilibrium, and in that vicinity we are considering we are having the solution y naught initial position, and this inside a ball delta, then we can claim that the mapping of this zt minus yt will also be inside a ball of radius epsilon in our image space, right? So in our image space we have that ball, and this is obvious because continuous dependence on the like on the right hand side function, if the f is defined, and we can do this, but we need more mathematical rigor, and for that we need the theorem which I am trying to tell you, like, and the theorem is, let f of t comma x be piecewise, this is very important phrase, piecewise continuous in t, and piecewise continuous in t and Lipschitz in x within that interval for all t belongs to that compact set t naught comma t1. This is very this is so real, na? Because time, how for a continuous time system you can claim that let us consider only the rational time. How can you exclude root 2, say root 2 second? How can you exclude root 2 second? It is not possible. If you are supposed to means cover up from 0 to 10 second, you are supposed to also calculate the value or consider the solution at root 2 second, at any other pi second. So it is not possible for you to discard them. It is not on your hand or not within your discretion. So t naught comma t1 has to be compact Lipschitz for all t naught comma t1, and now the function f is defined on this T naught comma T1 cross, this is a Cartesian product, we know about it, with a Lipschitz constant L, where this W belongs to Rn, is an open connected set. Let, why it is open connected and what is the essence of mentioning this, I will explain. Let, we are having two solutions, yt and zt be the two solutions, so we can write y dot is equal to f of t comma y, f of t comma y, with initial condition y t naught is equal to y naught, then we are having another one, z dot is equal to f of t plus, sorry, f of t comma z plus g of t comma z for all, like, sorry, such that z t naught is equal to z naught. Now, like the previous one, here we are having assume that yt, zt both belongs to that open connected set wt, sorry, w, not wt, although there is no harm, you can say wt, but let's make it w, for all t belongs to t naught comma t1. So one question that I am supposed to answer in the due course is why W is open connected set, what its implication and why it is so necessary. So what we will get that if this is true, then in addition we have introduced a function g. So g is such that g's norm, g's Euclidean norm is like is less than equal to mu for all t comma x belongs to that zone, right? For some mu greater than 0, we can write, this is very important, which I am going to write here, please pay your attention. We will exploit this in the near future, that this is, let me use different color. This is plus mu L exponential t minus t0 minus 1. This is true for all t belongs to t0 comma t1. Right, let us again revisit the statement of the theorem. Feeling very drowsy. First thing that we should know is that formal definition of connected set, and we will like to discuss the notion of connected set in the light of disconnected set notion. A topological space, we know what is topological space X, how and what are the conditions that should be fulfilled by a topological space. X is said to be disconnected, not connected, disconnected if it is union of two disjoint non-empty open sets. So an example, if or means not example, rather inference that we can draw is that if X is connected it cannot be represented by two disjoint open set, right? Two disjoint non-empty open set to X cannot be divided into two non-empty closed set. The only subset of a connected set that is both closed and open, also called clopen. Every time when I want an important discussion, I find myself at the bottom of the page. Clopen means closed and open is X and the empty set or null set, right? They they are the two subset of X that can be that can have these kind of things, right? Now, if you want an example, then we can have an example like if you take 0 comma 2, this is a standard subspace topology. So it is a connected set. Now you can break it. You can break it in this way. And see the beauty. This side it is neither closed nor open. This side it is neither closed nor open. So although the second set is closed, but means it is your topology is connected. You cannot represent it. And if you take their union 0 comma 1 union 1 comma 2, then that is this union is disconnected. Now, so any convex subset we have already discussed that is connected or simply connected. Let me find out a suitable example that can give you that which is not connected. Like an example that is not connected, say x is equal to 1 or so this is an example of like disconnected set. You can see here that whatever element you are having here is now it's fine. Now you will see that due to that element 1 is misplaced, you are having one set that is means you can visualize them in a two-dimensional plane. It is having x very close to 1 but not 1, and here it is very close to 1, slightly greater than 1 but not 1. So this set is disconnected. So I hope you get some idea about connected and disconnected set. Now in that light, let us study the means why that W need to be connected. What happen if we consider W is not connected? What is the essence? Like, even we not go for the rigorous proof, we should understand that why we say that W is an open connected set. Why not close connected, and why it has to be some in that way? See that the answer lies inside the question. Because if W is not connected, then first of all not open connected, then how you can define Lipschitz on that for means all t, it is Lipschitz in x, and from where you are going to pick up x, you are going to pick up elements of means this x vector from your set W. Now if W itself is not connected, so then it will be difficult for you, right, to means define that Lipschitz. The sense of Lipschitz will become difficult for you to define if you do not have W. And another one is that W is an open connected set, not a closed one. Is that we like how to say that we know that means there are several means argument we can place to define or sorry to justify to why we should consider open set instead of a closed set, but that I will discuss later. One idea I would like to give you, and I would like to hear it from you, that connected, all I have already discussed why it is connected, why it need to be open, that I need to know, means that answer should come from your side. Like I was expecting answers from several other questions, and they remain unanswered as far I remember. But still, anyway, though with this understanding, if it is an open connected set, then we are picking up two functions yt and zt such that both of them are solution of this one is first one is an equation, and the second one, like first one represent the unforced condition equation, and then the second one is forced one. Then what we can claim more, that this force part is also like bounded by certain positive number mu. Like the implication of this line is like whatever contribution will be given by your input together with your system, this z dot is solved. You can visualize it, this z dot is your rate of change of state, and that g t comma g z, we are not even sure that whether the system is affine or non-affine system. For affine system, we can take that z out, or means this gt will be only a function of time, and means like we can make it means not input even, like this gt comma z. Anyway, so let us consider that it is free from that. Now, here what we are trying to say, that this writing this line is basically put a bound on your gt comma x, and gt comma x is like both way bounded, upper bounded and lower bounded. Like gt comma x cannot go rush towards negative infinity, cannot rush towards positive infinity. It is bounded by mu. Now, under that condition, we are expecting the bound of a solution like in this way. So, this is the, and also one thing that is very clear to us, that it will follow, this will follow a certain decay rate for this one. So, we can prove that. The whole idea is that after proving, we can see that it depends on the initial point x naught, because y naught and z naught, both of them were defined in terms of x naught. If you have noticed it, how we defined it, see that here, that for all z naught belongs to x such that x naught minus y naught, that ball of z naught is defined in such a manner that it is already inside that ball, like x naught minus y naught. X naught is a fixed point for your system. Now within that ball you are defining everything, and from that epsilon delta, and then you give it a formal shape of theorem, so which state that the like solutions will be dependent on your initial values. Y naught, z naught, all these are initial values, right? So this we can prove using Bellman-Ronwall inequality that I have already discussed. So another thing what we can do is that we can study the aspect of parameter variation. However, in case of parameter variation, this way you cannot write. Rather, you have to consider the parameter vectors in here also. Like, what is parameter vector? What I am trying to mean by that parameter vector. Say, instead of writing this, you should write it like x dot is equal to f of t comma x comma lambda, where lambda belongs to Rp. It is the number of parameters that you have, right? Now obviously you can argue that what is so special. It can be same, but it is not same. Like if you take the example of RLC circuit, then lambda belongs to R3. You are having in lambda 3 parameters CRL. However, if you consider x belongs to R2. Obviously, you can club them. Like you can claim that the way they have, we can figure out one parameter from other. But if you study that equation, you will see that RL and C, they are having their separate contribution on that equation. So parameter, it will be very unfair to decide that the state equation define the equation, or the number of parameters present in our system. So this is the case. Now let me write down the theorem in a formal manner. Like, let we have f of t comma x comma gamma be continuous in t comma x comma and locally Lipschitz in x and it is uniformly continuous in t and lambda within a domain that is defined by this lambda 0. This is from nominal parameter. What is nominal parameter? Like you buy some RLC from the market, and before manufacturing, say, you note down their values, means at They are nominal values. And then during operation, it may happen that due to heating of R, your R value will change. Due to some other properties, your dielectric losses and other things, or over the time use, your C value gets means deteriorated or affected. So this happen, but whatever be the this lambda contains the actual parameters, and this lambda 0 is a nominal parameter. However, whatever variation happens, it always within, we are assuming that it is always within a certain bound, and that is quite obvious because then we can consider it within a range. Then obviously D belongs to Rn. D is a proper subset of Rn, is an again open. So you have to explain this open to me. Open connected set. Let y t comma lambda naught be a solution of that x this equation sorry with the initial condition y t comma y t0 comma lambda naught is equal to y0, that is again a member of D. Now suppose we are having this y t comma lambda 0 always belong to D, for all t belongs to t naught comma t1, then given epsilon greater than 0, there exists delta greater than 0 such that if z naught minus y naught, that is the two initial condition of two different run, and then here both are non, so it is dimension independent. So whether you are having p vector or whether you are having n vector, here you are getting the Euclidean norm that is less than delta. So within that means open ball defined by the radius delta, then there exists unique solution. This is very important, a unique solution z t comma lambda of that equation x dot f t comma x comma lambda defined on t0 comma t1 with T0 comma lambda is equal to Z naught and Zt comma lambda, that satisfies Zt comma lambda minus Yt comma lambda less than is equal to, or all t belongs to T naught comma T1. So once again, why it is open, you will answer. Then this is we are considering a region where it is the parameter variation cannot exceed this region. Then we can have a solution. Then we can have another solution, that is an unique solution, so that we will get this condition satisfied. So what we can draw here, we can have a very nice pictorial representation of this. Like you can have, say, T naught to T1, between which you are going to define the solution. You can have your best estimated solution, say this solution is Yt comma lambda 0. Then you can have a solution like this. Like it is like within that region you are having means band of solution, means a band in that space beyond which your solution cannot go, and that band is defined in comprises such t comma x that it is T0 comma T1 cross Rn, or you can write even D, such that mod x minus y t comma lambda 0 Yt comma lambda 0 is less than is equal to epsilon. This radius of this cylinder formed around your actual or nominal solution is governed by epsilon. So that's all. It's not all, but with this light of this, we'll continue our discussion on